Hello everybody. In this video, we're going to be looking at density curves in the normal distribution. Density curves. So before this video, we've been looking at how to explore quantitative data. And before, we've always said that we look at a graph, or we make a graph, usually a dot plot, stem plot, or histogram, and we observe the shape of that. And that's a number two, we look at that SOX, that shape center spread, any outliers, any significant gaps, any special features, anything like that. That's number two. And then we do numerical summaries. In this class, we've used one variable stats in order to look at all of the different, the mean, the median, the quartiles, the interquartile range. We look at that number summary to get the more specific detail about the distribution. Now what we're going to do is we're going to start to look at this idea of a density, and sometimes the pattern of a large number of data or observations in the, as the book says, we can use a smooth curve. We can use a density curve to describe it. Okay, so couple things about a density curve is a density curve is always above a horizontal axis. So there's always going to be some sort of horizontal axis. The whole curve, all of it, is going to be above that axis. In the area underneath that curve will always exactly equal 1. Okay? And this is going to show an overall pattern of the distribution, kind of a general idea of what the distribution has done. You've seen me do this in class when we've looked at a histogram or looked at shape. I draw a smooth curve over the dot plot to say oh yeah, this is generally skewed to the right, or this is generally symmetric. That's what we're going to be doing right now. Look at this example here. We have a density curve, and you can see that there's a histogram. There's a histogram here underneath. Okay, there's a histogram underneath, and you can see that histogram is not perfectly symmetrical. However, let me highlight here. If we highlight this this curve, we highlight this curve right here that the book is drawn. You can see that we're generalizing for the symmetric shape. And really, when we're looking at large groups of data, we're not really that worried about the minutia. We're not worried about the small individual pieces of data in most cases. We're really looking for this overall pattern to tell us, some feature of a population that we're studying. Okay? So we're not if we're looking at all of the heights if we're looking at the average height of men in the United States, we're not going to be worried that some men are some individual men are tall or some individual men are shorter. We're going to worry we're going to be concerned about the general pattern. Where does the middle fall? Where is there the most? What is the shape of this? And these density curves help us generalize, so we don't, and it helps us simplify the complex, vast bit of data by generalizing it into into that smooth curve, so we can understand just by looking at it what's going on. Okay, so one of the things that we do to help make statistics more understandable is make a graph that's easy to understand, and a density curve helps us do that. So when we have the mean and the median on a density curve, it's important to understand that a couple of things. One, the median cuts the data exactly in half, which means if I'm looking at a density curve and I can see the median, say down here in this, down here, we know that half the data is going to be on this side of the median, and the other half is going to be on this side. So 50% in the green, 50% of the data will be in the red. Now, if I look at even a skewed graph, I know that 50% of the data is going to be over here on that side of the median, and 50% of the data is going to be on that side of the mean, underneath the curve, okay? So even if it's skewed, we know the data is going to be split exactly in half. The number of data on the left of the median is going to be equal to the number of data to the right of the median. The mean, however, is a balance point. So if we look over here at this image, the mean is exactly where that distribution is going to be balanced on. So the weight of the data, and sometimes it's because like there's smaller numbers and really big numbers. The weight of the data is going to be perfectly balanced on the mean. Okay, so this triangle represents the mean. So if this number, if we identify the mean as too far to the left, we would see that the distribution is weighted too heavily to the right. And if it was off the mean, in the other direction, you could see it would tip the other way. So the mean is the perfect balance point. So, and that's just something to be noted, okay? Now, if it's symmetric, like it is down here, both that mean and the median are going to be in the same place. If it's not symmetric, like if the distribution is skewed to the right or skewed to the left, remember that the mean will always chase the tail of that distribution. So if you look down here in the skewed, the mean is to the right of the median. That's because that mean is following the extreme values here over on the right, okay? So it's chasing that tail, where the median's always going to remain slightly unchanged by extreme values in a skewed graph, okay? So what we have here is check your understanding. If you would please... Actually, I forgot to put an answer key on the other side of this. So I'm going to help you out right now. So let's explain why this is a legitimate density curve. We're going to look at some reasons why. Well, one, we can see that the entire curve is above this horizontal axis. So we have the entire curve, everything is above it, there's nothing that dips below. That's great. The other thing we're looking for is that the total area under the curve is equal to 1. Okay, so because of that, we know this is an appropriate density curve. So let's look at number 2. About what proportion of observations lie between 7 and 8? Well, so I'm going to look at the numbers 7 and 8. And go, okay, so there's 0.12 there. So what percent of the data? Well, I'm going to turn 0.12 into a percentage. So that's going to be 12% of the data, okay? So that's what proportion of the observations lie between 7 and 8? It's about 12%, okay? And it tells us in the graph. Trace the density curve. Well, I don't need to do that because I have what I have. Mark the appropriate of the median. Well, the median, I'm going to try to guess here where 50% would be. So we'll call this the median. Oh, sorry about that. This is the median. So if I were to draw the mean, which is number 4, I'm going to draw it slightly to the left here because that is going to be, remember, it chases the tail. So the mean is going to be less than the median, and that's because the graph is slightly skewed to the left. So because of that, the mean is going to favor the tail. The median is going to stay it's going to stay directly in the middle. Okay, so that's how we would do that. So the mean is the red line, median is the black line. Let's move on. So the normal distribution is the density curve of a symmetric single peak and bell-shaped graph, okay? That's what we're looking at. We're looking at the density curve of that. Now, when we describe a normal distribution, we're going to describe it with its standard deviation and the mean. Those are the two most valuable pieces of information when it comes to the normal distribution. Here's why. 1, the mean tells you where the middle is, okay? So if we look at these two normal distributions, both of these are normal, even though they look different. You can see that their mean is it tells us where the center of that graph is. The standard deviation, however, right here, the standard deviation tells us how tall or shallow that normal distribution curve is going to be. So a really large standard deviation is going to make a flatter normal distribution, okay, a flatter curve, where a smaller standard deviation is going to make a much taller curve, like you see on the right, okay? So if we're looking at the graph on the left, the standard deviation is very large, okay, or is larger, which is making the normal distribution shorter. It has less of a peak because the data is more spread out. Where if the standard deviation is small, like in the picture on the right over here, you can see that the small standard deviation is causing the normal distribution to have a peak, okay? Now, if we look down here, you'll see this notation, this n parentheses mu sigma. What that is that's how we name a normal distribution. Here we're going to see that says that n tells me the distribution is normal, the mu tells me what the mean is, and the sigma tells me what the standard deviation is. So that's how we give it a name and give the critical information about that normal distribution to our reader. So in every normal distribution, we have this rule, the 68, 95, 99.7 rule. Now, what it says is 68% are going to fall between the first standard deviations of the mean. So if I'm going to draw a quick normal distribution here. Oh, kind of breaking all the rules and good drawing here. So here's my mean. Here's one standard deviation. Here's actually, I'm going to just restart all of that. This is the worst picture. We're going to give that another try. So we're going to go here. And oh my goodness, that's so much better. So we're going to have, here's our mean. Here's our mean. We'll call it mu. And we're going to have 1, 2, 3 standard deviations. I'm going to just use the numbers -1, -2, -3. And I'm going to choose 1, 2, and 3. And those are standard deviations over there, okay? So what we're looking at is within one standard deviation right here, just one. And if this is a perfectly symmetric graph, what I'm going to know is that 68% of the data is going to fall within the first standard deviation. That's that 68, 95, 99.7 rule. Now, what that tells me is within two standard distributions, so here, if I'm over here and here, the area that's in between that, the percentage of the data here, is going to be 95. Okay? So between two standard deviations, we're going to have 95% of the data. And last but not least here, if we have three standard deviations right here, if we're out 3, we're going to capture 99.7% of the data, okay? Now, you can kind of think, you should be able to think here that if we were to go 4 or 5 standard deviations out, that we would be capturing almost all, if not all, of the data in the distribution, okay? So we typically only ever go out to 3 standard deviations from the mean, just because there's no real point in gathering all of the data most of the time. But that's this rule. So within one standard deviation, it's 68% of the data. Within 2 standard deviations, it's 95% of the data. And within 3 standard deviations, we're looking at 99.7% of the data. Okay, let's look at a really handy tool at times. So if we look at this example, what do we see here? So we see, let's zoom in a bit. So we're going to see, first thing that we see, I'll use my highlighter, let's use green. First thing we see is that we have a standard distribution, a normal distribution of 6.84 with a mean of 6.84 and a standard deviation of 1.55. So if we go down here and we look at the graph that they made, I want to highlight some key things here. So one of the key things I want to highlight is the mean. Okay, so we have the mean directly in the middle. We can see that that's 6.84. Okay, and then we have, if you subtract 1.55 from that, you'll get 5.29, you'll get 3.74, and you'll get 2.19. If I add a 1.55 to that, we would get 8.39, 9.94, and 11.49. So it's important to see how they create these graphs. And we start with the mean, and then we add standard deviations out in both ways, okay? And we do it 3 times on each side, 1, 2, and 3 standard deviations. So the first question is, what percent of the ITBS vocabulary scores are less than 3.74? Show your work. So we can see that 3.74 is right here, okay? And we know that that's 2 standard deviations away from the mean. Now they do something tricky. They don't just ask what is in between the 2, because that would easily be 95%. They say, what's less than 3.74? Well, here's what we're going to do. So we know that all the area underneath the curve is equal to 1, okay? What we're going to then do is subtract or we can, if we're thinking like percents, it's 100% of the data. Okay, so what we're going to do is we're going to subtract 95 from it, because 95 is this area that's highlighted in red right here. That's that area right here. So and we know that 95% of the data falls between the 2 standard deviations, the second standard deviation. So if we subtract that, what we're going to get is 5%. Okay, now that 5% is going to be split in this over here, this green chunk, and the green chunk we're actually trying to find. It's split in half. So what do? Well, we divide that by 2, and our answer is going to be 2.5%. Okay. It's going to be 2.5%. And that's how we do that first question. What percent falls below that? Well, I used my standard deviation rule, and I said, okay, 2 standard deviations, that's 95% of the data. Subtract that from 100. That leaves me with 5% shared between 2 ends. Well, since it's shared between 2 ends, I can divide by 2 to find one of the ends. Okay? So let's look at the next example. The next example is a little trickier. So we're looking at, okay, what percent of the scores fall between 5.29 and 9.94? Now we can see in one of the lines we're 1 standard deviation away. In one of the lines we are 2 standard deviations away. Okay, so what we want to figure out is what's the area. What area are we looking for here? Well, we're looking for that red section and that green section put together. So we know that that's about that's going to be 68%, because of the 1 standard deviation. That's the red. If we look at that, so we know that that's going to be approximately. And if you look at the example, it does a really good job at showing us. So if I look at so that red, we know that that's going to be included, and that's 68%. Now what we're going to need to do is figure out, okay, what is this chunk that I'm highlighting here in black? What is that chunk worth? Well, we know with the 2 standard deviations we're 95%. So if we take 95 and subtract 68, we're going to get what these 2 pieces are going to be. Okay, the 2 pieces that I'm going to highlight in black. So that's going to be, then if we cut it in half, okay, if we cut that in half, That's going to give us 1, and that's going to give us the 1 that we want. So that's going to give us if we do that math, 95 minus 68 divided by 2, that's going to be 13.5. Now, we're not quite done yet because we're looking for, or actually the problem is asking for this whole area right here. I'll highlight it in black instead of filling it in. So we're actually looking for this area right here, which is, we know that's part of that is the 68%. And then the other part is the part we just found with the 13.5. So we're going to add 68 to 13.5. And that's going to be 81.5%. Okay, that's how we can navigate some of these 68, 95, 99.7 rules. So you're going to get more practice in just a minute. Make sure some of the key things that really help are drawing the picture and shading in the areas that you need to find. Some people just try to do this in their brain, and it can be really tricky without the visual thing, and without the visual representation. And one of the strategies that we've been learning when looking at and discussing statistics and numbers and data is we should always draw the picture. That's something that we should do here, especially as we're learning. Sometimes it's going to be very, very easy, very, very straightforward. You may be able to figure it out. But a more complicated problem like B, you really want to draw that picture out and use your all your senses, use your brain, use your eyes to figure out, use some drawing, use some tactile to figure out that, because it might be hard to see on its own. So draw the graph. Shade in areas so that you can figure out what areas do I need to subtract. If you can do that, it's only a matter of addition and subtraction, and it's going to be a really easy puzzle for you to solve, okay? So just keep that in mind. Draw your pictures. So there's going to be a check your understanding. I put a little sketch in just in case people were confused before. So remember that this value right here is going to be the mean, and then these are going to be your standard deviations. I added 2.5 because that's what was up here. I added 2.5 to each side of that mean. I just kept on adding 2.5 3 times to the right, and I added 2.5 3 times to the left. And that gave me kind of my distribution and mean and standard deviations, okay? So look at the questions. I did number 1 for you, and what you're going to do is numbers 2 and 3, okay? The answers are on the next slide, so pause the video real quick, see if you can figure it out, and we'll see you when you come back. Welcome back. Here are the solutions. Remember, if something in the video if you're struggling with something in the video, reach out, let me know, shoot me an email if you're in one of my classes. I want to make sure that you are all set as you're going through this. If I don't get back to you right away, I will. So we can Zoom, we can work through a couple of these. Once you get a couple of these under your belt, you're going to find that you're okay. So, and we have some practice with them in the homework. So, yeah, reach out, please, and we'll help you as much as we can. Okay. The standard normal distribution. Now, one of the things that we do, and we talked about this in our last video, is we can standardize a distribution using z-scores. And what this is going to do, it helps us communicate a distribution across many fields, okay? So you might have, if you've taken AP Bio or AP Psychology or just biology and psychology, you might have heard the words mean and standard deviation before. Those commonly show up in those fields and fields with research. And the reason we use standard deviations and not like data values is because everyone in all the industries, that like every statistician, every scientist should have a basic understanding of what that mean and standard deviation is, like the definition. So standardizing gives us a standard normal language, okay? And again, the reason we do how we do that is we use this z-score formula to transform the data values into z-scores, and that's what standardizes it. And remember, a z-score is like the decimal it's basically a standard deviation, but it doesn't just have to be 1, 2, or 3. It can be all the numbers in between 1, 2, 0, 1, 2, and 3. Okay, it can be all those numbers. Now here, it has a special name. Normal, standard normal distribution is NEN for normal, and the mean is going to be 0, and the standard deviations are going to be 1. Okay, and again, we do that to help us communicate information about a distribution across all fields that need to see it. Okay, standardizing it makes it easier to communicate. So what we're going to be getting into is finding areas in any normal distribution. Now, if you read this, it'll say that it'll mention like a table A and finding a z-score and all of that. That is one way of doing it. However, what we're going to do is we're going to use, it also says, or use technology to find the desired area underneath the curve. And we're going to use the normal CDF command, okay? The normal CDF command is going to be one of our best friends. Normal, I'm going to write it, I love it so much. Normal CDF. This is going to be one of the best commands on the calculator that we use because it's going to take a process that can be slightly complicated or convoluted, and it's going to make it very succinct, and it's going to make it happen very fast, okay? And that's going to be a really powerful tool throughout our entire class. Being able to find areas underneath the normal curve very quickly is going to be critical. Let's look at it. Let's actually look how to get to normal CDF. Now we have, I've given you this tool. Is kind of walk through, but I'm also going to show you kind of using this, what calculator buttons to use. So the first thing you're going to press is second, and then you're going to press vars. So you're going to press second vars, and you're going to see a couple options. Number 2 is normal CDF. So you'll press second vars, and that's going to be. That'll give you the normal CDF option. In there, you're going to see the lower bound, the upper bound, the mean, the standard deviation. So we'll talk about that a little bit later in an example. But in order to get there, you're going to press second vars, and then the second option is going to be normal CDF. And we'll go into that a little bit more in just a second. Okay, so let's look at this example here. So this one talks about Tiger Woods, okay? This one talks about Tiger Woods and in his ability to drive a ball. How far can he drive a ball? Well, Tiger Woods' driving ability in this example says there is he has a mean drive, for sure, that's for sure. He has a mean drive of 304 yards with a standard deviation of 8, which is incredible. That's an incredible drive, everybody. So then if we look over here in the graph, okay, so they drew the picture, very important, and they did it for us, so we won't waste time redrawing it. But they're looking for the area, it says what percent of Tiger's drives are at least 290 yards. So we want to know what percentage of drives are 290 yards or better. Okay, so what we're going to do is we're going to use that normal CDF, okay? So we're going to use our calculator, and just like what I showed you in the last slide, we're going to press second vars in option 2, okay? And that's going to be normal CDF. So you press second vars and you'll normal CDF. And what you're going to see is this, you're going to see some options. You're going to see the lower, you're going to see the upper, you're going to see the mean, standard deviation, and paste, okay? So the lower bound is the lowest value it can be. In this problem, that could be 290. So we're going to put 290. Now the upper bound, what we're going to do when we're finding the whole thing and it's all the way up, we're not going to stop at like any of the standard deviations. We're going to put a really large number. So I'm going to put 10,000. Okay, what I like to say is put a 1 and a bunch of zeros after it. So we have the lower bound at 290 and an upper bound of 10,000. Now, if this were to go the other way, if we were looking at the low end, you would switch these numbers. The lower bound would be the 10,000 and you would make it negative. Okay, but right now we're looking up. So the mean is going to be 304 because that's what the information says. The standard deviation is going to be 8. So, and then you click paste, go down to paste and hit enter twice. Okay, so I call it paste. When you click paste, it's going to make it's going to bring it to like the regular calculator screen, and then you need to enter in that calculation, and it's going to give you that area. So in this case, it's going to be 0.9599. So what percentage? It's going to be approximately 96%. Okay, so when you hit that paste, you should get 90.9599 when you enter that. So that's approximately 96%. Okay, and that's how we can use normal CDF. Now let's look at another example of this powerful tool. So let's look at some of the harder questions we were looking at earlier, okay? So we're that 90, where we had to do quite a bit of math. Well, we can use normal CDF to really help us manage some of those more complicated problems. So this one says, what percentage of Tigers drives travel between 305 and 325? Okay, so you can see we're not in between any standard deviation, so we can't use that other rule. What are we going to do? Well, we're going to go to normal CDF, so second vars, and then we have the lower option, the upper, the mean, the standard deviation, okay? So the lower bound is going to be the lower number, 305. The upper bound is going to be 325. The mean is going to be what it was before, so it's going to be 304. That hasn't changed. And the standard deviation is going to be 8, okay? So we enter that information in, we click paste, and what that's going to give us is 0.4459, or approximately 45%. So what percent of the drives travel between 305 and 325 yards? It'll be about 45% of those drives. Okay, a little less than half. All right, and again, that's the power of normal CDF. Very quick, very powerful tool. You can see the other options kind of above you. So this is the work that we do down here. And if you were to do this by hand, this is all the work that you would have to do in order to figure that out. So we really like this calculator option because of how fast and how powerful it is. We don't have to calculate z-scores. We don't have to use a table. It's absolutely incredible. Okay, so we're gonna use it. We're gonna love it. It's gonna be critical to our success. So now we've learned how to find the area. Now what we're gonna do is, how do we find how do we find a value if we're given an area? How do we go backwards? Okay, so what would be asking here is, say I knew this area right here. Say I knew this area. What value is going to give me this area? Okay, and that's the question that we're going to be asking. All right, that's the question that we're going to be asking. Now, we're going to be using a tool called inverse norm in our calculator. Just like normal CDF, inverse norm is incredibly powerful, and it is option 3. Now, one thing that needs to be noted is inverse norm only works this way, okay? Inverse norm only works to the left. So if we're going to find areas like I asked before to the right, like here, you're going to have to use like subtraction once you figure out, you're going to have to subtract the value from 1 once you figure out what that value is, okay? So let's move on here. Inverse norm. I forgot I put this in here. So inverse norm, again, second vars, and it's option 3, okay? It's the third option down, and you'll find inverse norm. And that's going to be able to help us find our value for that norm. So let's look at an example here. So the cholesterol in young boys. So we have high levels of cholesterol increase heart disease. So we looked at a bunch of 14-year-old boys and we found their blood cholesterol. We found some information about that. We found the mean to be 170 and the standard distribution to be 30. Okay, so now when we're looking at the mean and the standard distribution, now we can kind of use inverse norm and go from there. And what we're doing is, what's the first quartile of distributions in the blood of cholesterol? Okay, so first quartile, what does that mean? Well, that means what's the first 25% of the data? Okay, that's what we're looking for. What's the first 25% of the data? What's lucky here is inverse norm works to the left. Okay, so we're not going to have to do any subtraction. We're just going to have to do the calculator function. Okay, so what you're going to do is going to go second vars, go to option 3, inverse norm, and it's going to say, okay, what's the area? What's the mean? What's the standard deviation? Okay. Well, the area is not, so we're got to be careful here. Some people make this mistake. The area is not 25. It's 0.25. Calculators don't typically like to work in percent. So we have to turn it into a decimal. The mean is 170 and the standard deviation is 30. Okay. Here we go. 0.25, mean 170, standard deviation is 30. Paste, paste, paste. Get all my answers here. And that value, what it's going to kick out is 149.8. It's like 147.6, 149.76, but we're going to use that. So that's the value there. So what we would say is the first quartile of blood cholesterol levels is about, well, it's they even round up in the answer down here. It's about 150 milligrams, okay? So 20, and we know that quartiles and percentiles relate to each other, which means if you have a blood score, a cholesterol level of 150 milligrams, then you have more cholesterol in your blood than 25% of the other people in the study. Okay, so again, I'm just putting that into context so we understand, because that's important. So here's your check your understanding. Again, pause the video. The last slide will be the solutions here. So pause your video, try these. Again, this is going to be normal CDF or inverse norm. I'll give you a hint here. In the first two, we're looking for percentages. We're looking for the area. So we're going to use normal CDF. The last one, however, the blue one, we're going to be looking for a distance, a particular data point. So that is going to be inverse norm. So the first two are going to be normal CDF. The third one is going to be inverse norm. So we'll see you at the next slide. And once you pause, and you'll start it up, and we'll see you there. Welcome back. Here are the solutions. Again, any questions, make sure you hit me up with an email. I really appreciate you watching this video. I know these are long, but these are our lecture. These are how we can dispense information to you. So, I apologize, but also at the same time, it's important that we watch these videos and partake in our class. Okay. So, I hope that you learned a lot. And while you're doing the practice, please feel free to reach out and ask any questions. and I will answer them promptly. Okay, have a great day, and we will see you later.